Hello all. Today we will discuss three-phase EMF generation. In my earlier lecture, I have already discussed the generation of a single phase. So let us first discuss that what is the difference between a single phase and three phase. In a single phase, we have seen that we have a live wire and the other wire is neutral. And what we do, if I write here, one is the live wire, another is the neutral. What we do, we connect our devices, especially at our home, which we find it to be the single phase supply. So what we do, we connect our appliances across these two terminals and we get the, or simply we connect the load over here and we get the output. But in the case of three phase, we are going to have three phases, means this live wire will now be replaced with the three different wires that will be named here as red, yellow and blue wires, and one fourth wire will be there, that is the neutral one. So now we are having the option to connect our machine, or if I say it is used in the industries, so there we have the high load machines. Industries, we have three phase of supply where we have heavy load. So for this heavy load we require these different phases. So the next question is that why we need it, why these heavy machines require three different phases. So if I talk, or if I discuss a single phase, in the single phase we have alternating voltage. This alternating voltage changes its value from 0 to the maximum, let this voltage be Vm, and then again back to 0, and then to the negative maximum voltage represented here as minus Vm, and again back to 0. It means in a single cycle it changes its value from 0 to maximum, then to negative maximum, and back to 0. Or if I say, if this frequency of the signal is 50 hertz, then approximately in 1 second, in 1 second it crosses this 0 mark around 100 times. So now assume that if we have connected a heavy load across such supply, then that load will be given or get the voltage equal to 0 in 1 second, approximately around 100 times. So just to avoid that, we needed three-phase supply so that that load will not be reduced to 0, or will not, the output across it will not be reduced to 0. Now look here, what is this three-phase supply? In this three-phase supply, one is this red. I will assume this to be my reference signal. So you will find this signal to be exactly similar to that in the live wire or the single phase. But this yellow signal or the yellow wire will have again a similar sinusoidal signal, but it will be phase shifted by some angle. So I will say here this angle is phase shifted by 120 degree. So you will find here that exactly after 120 degree this signal will start. So definitely the signal will start from here and then it will increase and so on like this. And similarly the blue one will be phase shifted with reference to the red one by the 240 degree. So you will find again this to be shifted by 240 degree, and you will find it to be first crossing this value like this. So these three different phases will be there in these three different wires, and the fourth one is the neutral wire. Definitely when we connect any load we need the neutral also. So now the point is that we need these different phases so that at a single point this all the three phases will not reduce to 0. For example, if I assume this point where my red line is reduced to 0, similarly at this point also red line is reduced to 0, and over here also this point reduced to 0, I will name them as 1, 2 and 3. So if I look at this one point, the other wire, that is the yellow one and the blue one, are not equal to 0. It means if I connect any load, or if I connect this three-phase supply across a heavy load machine, then definitely the value will not be reduced to 0. Although one of the phases may lead to 0, may give you the out voltage equal to 0, but the other two will not be 0. Or you can say that the resultant of these, the resultant of these three wires, three voltages I must say, because these wires are containing the voltages, can never be 0, can never be 0 at the same time, or at any instant of time, at any instant of time. So that's why we prefer to have three-phase supply in the industries, or especially where we have the heavy load machines. So in the last lecture we have already discussed that how we can generate the single phase EMF. There we have made use of this Faraday law. In that Faraday law we have seen that if we place any conductor inside a magnetic field, their magnetic field is over here in this diagram is produced by this north and south poles of the magnet. Definitely the magnetic fields will be, magnetic lines of force will be from north to the south. And if I place any conductor inside it, let us assume this is my conductor, then definitely if I move this conductor in the anti-clockwise and the clockwise direction, the magnetic flux lines crossing this conductor will change. For example, if I take this case where the perpendicular of this conductor, let me draw it with a different color, the perpendicular of this conductor is in parallel to the magnetic lines of force, or simply if I say the angle over here is angle between perpendicular of conductor to magnetic lines of force, or simply magnetic lines, magnetic field lines I must say. So magnetic lines, so if this angle is, for example in this case it is 0 degree, then you will find that the maximum magnetic flux will be there. And if I denote magnetic flux with the phi, I will denote this point to be as phi m. Whereas if I draw it with a different color, if for example my conductor is in this place or in this direction, then definitely the perpendicular of this conductor, which is now this one, will make an angle 90 degree with the magnetic lines. So next I will write when the angle is 90 degree, then I will assume that very less or minimum magnetic lines will cross this conductor and the flux density is very small, denoted over here is almost equal to 0. And definitely when there will be a different angle other than the 0 and 90, for example this one, so at this point the magnetic lines will be somewhere in between 0 and phi m. So at some angle or some theta which is less than 90 degree but greater than 0 degree, in that scenario I will say my magnetic flux phi will be less than phi m but greater than 0. So it means if I made any conductor to rotate inside the magnetic field, then the magnetic flux will change, and that magnetic flux will produce an EMF that is given by E is equal to minus EM sine of omega t. Right? So this EM is nothing but depending upon the value of the magnetic field lines, magnetic field is strong, the value of the B will be large, so this EM will be different. Also it depends upon the number of the turns in the conductor, because this conductor is consisting of a coil. So we have already discussed this part, we have already generated this EMF, E is equal to minus EM sine omega. So kindly go through that video before studying the three-phase EMF generation. So I assume that this point is clear to you, that how we have obtained this E is equal to minus EM sine omega t. Now in addition to this single phase, we are having here more than one phase, or simply three phases are going to be there. So how these three phases will be generated, as I want here total rotation is 360 degree, so the three phases will be there, means three conductors will be there inside the magnetic field. So definitely they will be generating a phase difference of 120 degree. To generate this phase difference of 120 degree, they must be aligned 120 degree to must be aligned at a distance of, or there will be a displacement of 120 degree between them. For example, instead of single conductor over here, I am going to have three conductors, one with the red one, other is called as yellow, and third is the blue one. So these are the three conductors. Now these will be rotated. For example, I am rotating here now in the anti-clockwise direction. So according to the Faraday law of electromagnetic induction, we know that whenever a coil is rotated in the magnetic field, there will be sinusoidal EMF induced in that coil. So that EMF will be induced in this red one also, Y one also, and the blue one also. But if you look at the displacement between these, if red and yellow are compared, there will be a displacement of 120 degree. If yellow and blue is compared, there will be a displacement of again 120 degree. But if I compare red and the blue one, there will be a total displacement of 240 degree. It means definitely when they are displaced with different angles, the EMF induced by them will be different. So if I look at these three different waveforms, you will find here this red one corresponds to E is equal to ER EM sine omega t. ER is equal to EM sine omega t, which I assume here to be the reference one, that is red one, which is at a 0 degree phase shift. Second, I am going to discuss here the yellow one. So yellow one Now the yellow conductor, yellow coil over here was displaced by an angle of 120 degree with reference to this red one. So it means definitely the waveform or the wave that will be generated by that conductor or by the coil will be displaced by the angle of 120 degrees. So you will find here exactly the difference of 120 degree. So this point in with reference to this red one was displaced by or by is having a phase difference of 120 degrees. So this is having a phase difference of 120. And similarly, if I look at this blue one, so blue one is crossing this zero or starting from here. So if we compare this with the red one, it will have the phase difference of 240 degrees. So by simply having three conductors inside a magnetic field in place of one conductor, in the case of single phase, there will be generation of three phase supply, but we have to make sure that these three conductors must be displaced by an angle of 120 degree with reference to each other, or with reference to the red conductor they must be displaced by an angle of 120 degree for the yellow one and 240 degree for the blue one. So by this we can say that we are going to generate here three EMFs. I will name them as ER for the red one equal to EM sine omega t. Second one is EY, which is equal to EM sine of omega t minus 120 degree, right? And the third one is EB, that is equal to EM sine of omega t minus of 240 degree. So you all are aware of this, why I'm using here minus 120 degree, because on the omega t axis it is shifted towards the right hand side. If you look at this one, this part or this rising of this red one, it in the yellow case it is shifted over here to the right hand side. So definitely it is omega t minus of that angle. So that angle is 120 degree. Now this is simple basic of the EMF generation. What we have done, we have simply make use of the Faraday law of electromagnetic induction, where it simply says that whenever a coil is rotated in a magnetic field, there is a sinusoidal EMF generation induced in that coil, which is given by EM sine omega t. Right? As these three coils are rotating in a uniform magnetic field, तीनों के लिए हमने same magnetic field रखी है. It means definitely if they are having the same angular velocity also, then the waveforms or the sinusoidal signal or the EMF generated by them will be of the same amplitude. So all these three waves will have the same amplitude equal to EM. So maximum one is the EM, and they are shifting with respect to the sine of omega t. Only displacement, or you can say in the case of sine signals, we will say that there will be a phase shift only, rest of the things are the same. Now if I compare the single phase and the three phase supply, so three phase supply is consisting of three conductors, or simply I can say here three coils, whereas in the case of single phase we have only the one conductor or the one coil. These are the diagram or the wave shapes. Then if I say here that we require only two wires for completing the circuit, one is the live wire and second is the neutral, whereas in this case we are going to have the four wires, one is red, here second is yellow, third is blue, fourth is the neutral. The voltage that we got through the single phase is 230 volt. Normally this is the voltage that we receive at homes because we got single phase at our homes, whereas at the industries the voltage is around 415 volts. Then next one is the name given to this. Split phase is also the second name of the single phase, whereas there is no other name for the three phase. Then the network by this single phase is always simple, whereas it will be complicated because more than one wires are involved. If you look at the losses, there are high losses in the single phase, whereas in the three phase there are less losses. This is again a diagram of the power supply connections. Then if you look at the efficiency, these single phase are less efficient in comparison to the three phase. They are less economical also, whereas if you look at the uses, I have already told you, for home appliances we use single phase. For the heavy load where we are going to use the heavy machineries, we are going to have the three phase. So this is the basic idea related to the single phase and the three phase of power supplies. So next I want to discuss today about two connections, namely as the star and the delta connections. The star and delta connections are already known to you, but still I will give you a brief idea, because now in this lecture I'm going to tell you about few definitions which are related to it. We are going to use them for the balanced and the unbalanced load in the next lectures. So if you look at the star connection is nothing but, again we are going to have here three phase, so definitely three coils will be there. So look at this, this is the first coil. Use a different color over here. So this is my first coil, This is my second coil. I have denoted them with a different color just to make you understand better. So these three coils are all connected to a single point, or you can say that one end of these all three coils are connected to a single point named here as the N, or we can simply connect here a neutral wire. So this is your neutral wire over here. And the second terminals of these coils are connected to the different terminals. For example, if I consider this red one, it is connected to the R terminal, where I'm going to get the R phase or the R line current or the line voltage, whereas second one is for the blue, where I'm going to get the B line voltage or the B phase voltage, and third one is the yellow, where I'm going to get the yellow line and the phase voltage. Now, similarly, in the case of delta also, there the delta connection will be there. It looks like a triangle, but the connections are a little bit different to that of the star. In the star, all the three coils are connected to a single point, whereas in this case, no, all the three cannot be connected at a single point. Only two are connected to a single point. For example, if you look at this blue one and this red one, they are connected to the one terminal. I have named this terminal as 1, whereas blue and yellow is connected to the 3 terminal, and red and the yellow is connected to the 2 terminal. Now over here, this 1 terminal is called as the red one, 3 terminal is called as the blue one, and 2 terminal is called as the white terminal. And according to that, we are going to calculate the voltages and the currents across these terminals, red, yellow, and the blue. Right? So this is the basic idea of the star and the delta connections. Now, the terminologies that I want to use is nothing but simply the values of the voltages and the currents across these coils or across these terminals. Terminals are only 3, that is red, yellow, and the blue. So there is a sequence we always follow, that is red, yellow, and blue. Red is always at 0 degree. There is a phase difference of 120 degree between yellow and red, and between blue and red there is a phase difference of again of 120 degree. So the sequence that we will follow is either red, yellow, blue, or in some of the books you will find this sequence to be as blue, yellow, and the red. These are one and the same thing. You can use it in either way, right? So now next I want to use here is the phase voltage and the line voltage. So let us discuss what is this phase and the line voltage. This phase voltage is nothing but the voltage across either phase winding or the load terminal. So if I just take the case of this star connection, so this is my coil. If I take this red one, this is my coil. So the voltage across this coil will be called as my phase voltage. Phase voltage. And as it is connected to the neutral terminal, it is also called as VRN, because this is the phase voltage of the red coil with respect to the neutral, so it is called as VRN. Similarly, if I talk about the blue one, it will be called as VBN, but this is the voltage which is existing across only the coil. Coil के across the voltage है उसको आप कहेंगे phase voltage. So we will have here 3 different names: VRN, VBN, and the VYN. VYN. Right? This is for the star connection, whereas in the case of delta connection, it is between the two phases. For example, if I talk here about this VB, or the voltage across the blue coil, so definitely this voltage will be across terminal 1 and the terminal 3. Terminal 1 is nothing but your red one, whereas terminal 3 is your B1. So from here I can say that the phase voltage VB will be the voltage across the points or across the R and B, right? Whereas if I talk about the VR, red one is between R and Y, so it will be R and Y. And similarly for the yellow one, the phase voltage of the yellow coil is between yellow and blue. So in this way you can calculate the phase voltage for both the delta and the star connection. Now next, or similar to this, is the line voltage. Now line voltage is the voltage across any two terminals. It is not across the coil. The coil voltage is called as a phase voltage, but line voltage is across any two terminals, and it is generally denoted by the value VL. So we have the voltage VL common for this. So if I talk about the voltage of the red coil or the red terminal, so the VRY will be the voltage, line voltage across R and Y. So this is the first line voltage VRY. As the name is R and Y, so it will be between R and Y. Second is V by B. So it will be between Y and B, and third one is the VBR, which is between the blue and the red. Right? So this is the difference between the phase voltage and the line voltage. Third one is the phase current, and similar to this will be the line current. Now, if you look at this diagram in the delta connection, I have here a current IB. This is my current IB. So this is the current that is flowing through this coil, blue coil. So this will be my phase current. जो coil से current होगा वो phase current होगा, जो coil पे cross voltage होगी that will be the phase voltage. So this is my phase current, right? Similarly, for the yellow coil, the phase current is IY, and for the red one it is the IR. But if I want the line current is the current through the terminal. What is the terminal? It is red, yellow and blue. These are my three terminals. It means the current flowing through this terminal, this one is called as the line current. Now, if I take this blue terminal, it will be the IB current. If I take the yellow terminal, it will be IY. If I take the red one, it will be my IR. Whereas if I consider it in the case of my star connection, I can say here that IR, which is the current, phase current across the red coil, is almost equal to the current across the R terminal, because they are all connected in series. तो जो IR आपका phase current है वही आपका क्या होगा, IR line current होगा. तो स्टार के केस में we can say here IR phase current is equal to IR line current in this diagram. Similarly, the line current IB, that must be equal to the phase current of the IB or the blue coil. Similarly, IY, line current of the yellow terminal, is equal to the phase current of the yellow coil. So in this way, depending upon the type of the star and delta connection, you can have some assumptions also. But my point in today's lecture is just to tell you about the line current and the phase current. So I guess it is clear to you. We have just discussed phase voltage, which is the voltage across the coil; line voltage, which is the voltage between the terminals; phase current, it is the current through the coil; line terminal, it is the current through the terminals. Now next one is the phase sequence. Phase sequence is nothing but, as we said, that we are going to have the three coils, and all these three coils are phase shifted by 120 degrees. So we need to follow an order in which these three coil EMFs or the currents attain their peak values. It's called the phase sequence. So now if we look at this diagram, I'm going back to my diagram. So if I see, the peak value is first achieved over here by the red coil, right? This is the first one. So I will say that my sequence will be R. Then it is achieved by this yellow coil. So I will say Y, and third by the B. So this sequence is RYB. Don't get confused over here, as in few of the books you will find this EM to be exactly over here. So this is not achieving its maximum value over here. Whenever we need to find the maximum value, we need to first see that it has crossed the zero mark or not. For example, in the red one, we have seen here that it has crossed this zero mark. Similarly, for this yellow one, we have seen it has crossed this zero mark. Similarly, for the blue one, it has crossed this zero mark. Only after crossing the zero mark, we will consider the maximum voltage. You can't say that blue has achieved its maximum voltage. No, this is wrong. Blue is only achieving its maximum voltage at this point, and yellow is at this point, and red is this point. So if I arrange that which is coming first, so it is first is red, then yellow, and the third one is the blue. So the phase sequence over here is the R, Y, and B, which corresponds to the three different colors. Then next we are going to discuss about few balanced and unbalanced systems. So this terminology, or this is important to understand. What do you mean by a balanced system? A system is said to be balanced if the voltage and currents in all phases are equal in magnitude and displaced from each other by equal angles. So as I am saying that there is one current IR, there is another current IB, and there is third current IY. Similarly, I am saying that there is a phase current IPH, or I have denoted that with the value of IRPH, right? So this is these three are for the line, and then I will again say IR, IB, and IY. These are for the phase. And similarly for the voltages, VR, VB, VY, right? So these voltages and the currents should be equal in magnitude. All these three must have the same magnitude. means IR must be equal to IB, it must be equal to IY. Similarly, in the phase also, IR must be equal to IB equal to IY. Similarly, this phase or the line voltages, VR must be equal to VB equal to VY. So if this is there, or you can say these all the phases are equal in magnitude and displaced from each other by the equal angles, means the angle is 120 degree, then that kind of system is called as balanced system. So that is possible only when we are having the equal magnitude and equal number of turns in the coils, or the length of the coil must be same, or the rotation of the coil inside the magnetic field must be same. In these cases we will get the balanced system. But we can also have an unbalanced system. In the unbalanced systems, these phases may be different. Maybe they not be displaced by the 120 degree. They may be displaced by some different angles. For example, if one is at this one, second may be at a 90 degree, and third may be at the 45 degree. So if this case must be there, so इन दो केसेस में हमारे पास जो है फेज डिफरेंस जो है होंगे वो डिफरेंट आएंगे तीनों के, या एक हो सकता है 0 डिग्री पे है, दूसरा 90 पे है, तीसरा जो है वो मैं 180 के आसपास ले लेता हूँ या 240 के आसपास ले लेता हूँ. सो इन दोस थ्री केसेस the phases will be unequal in magnitude because they are displaced with each other by the different angles or by the unequal angles. In that will result into the different voltages and the currents. In that case, IR will not be equal to IY and it not be equal to IB. Similarly, VR will not be equal to VY and it not be equal to VB. Right. So this kind of systems are called as the unbalanced systems. Now next definition is the balanced load. Balanced load is nothing but the load in all phases are equal in magnitude, as we are going to connect any load across these two terminals. For example, if I take the case of this one, in this diagram, if you see that I am going to connect here the load. So if I take a red line and a neutral wire and I am going to connect a load over here, let this load be RL. Similarly, I am going to take here a yellow line. Okay, let me. I'm going to take here, this is my red line. Then I'm going to take a yellow line over here. And across this also I'm going to connect a load. So if this load RL is different than the load of the yellow one, that is RL dash is different from the RL, then in that case I can say my system is the unbalanced load. And if these are same, then I will say it is the balanced load, right? Whenever we need to have discussed these loads, we always discuss the power factor. Means when we say that the load will have the same power factor, equal currents in them, then we will say it is a balanced load. When we will say we have unequal power factors and the currents in them, then it will be the unbalanced load, right? So this is all about the basics of this three-phase EMF generation and the difference between the three-phase and the single phase and the terminologies that we are going to use in the next lectures. So any queries, just let me know. That's all. Thank you.